All right, let's go ahead and look at checkpoint 13. So we have this graph here. I want to find the area between these two curves. So before I do that, though, the first question here asks, basically I'm giving you a hint. So why would I want to set up this integral in terms of y instead of in terms of x, like what you have mostly done? So let's think about this. If we were to set up this integral in terms of x, let's think of what those rectangles would look like, those dx rectangles. Well, if I did those dx rectangles over here, like to the left of this like crossing point, then what I'm going to have to do is I'm going to have one integral that basically compares the height of this curve to itself. But if I have these rectangles over here, then I'm comparing the height of this curve, this parabola, to the height of this line. So basically, if I set up this integral, in terms of x, then I'm going to have one integral for to the left of this dashed line and a different integral to the right of this dashed line. So I'm going to need to have two completely different integrals. On the other hand, what if I set this up using dy rectangles? So if I just let y change by a little bit, I don't want to make it that thick. So I have these long but thin horizontal rectangles. So no matter where I draw rectangles like this, where's the left end of these rectangles going to be? The left end of these rectangles is going to be dictated by the parabola. It's going to be dictated by the curve. Where's the right end of these rectangles going to be? The right end of these rectangles are going to be dictated by the line. So because the left and right ends of all these rectangles can be dictated by, consistently by the curve and the line respectively, that is what lets me get away with doing only one curve, or not one curve, one integral here to find this area. So lots of ways to kind of describe that, but that's one example of basically how to justify why using y as your independent variable is probably a better choice. So now that we have that, let's go ahead and do this. So let me give names to these things. I will call the red parabola f of y, and I will call the blue line g of y. So what I want to do here is I want to set up an integral. So that's what part B is. I kind of did A verbally. So typically what we have to do when we find an area between curves is set up an integral. And the language that you probably heard in the videos is what we typically do is we do the upper curve minus the lower curve. But that really only makes sense when we're subtracting curves that are written in X. So I'm going to substitute that with some more general language. We're going to subtract the greater curve minus the lesser curve. And if we're talking about left versus right, then what's greater? If you're looking at a graph, then the greater values are going to be right. So which one of these curves is greater over this interval? That's going to be G. Because like we said just a few minutes ago, the right end of these rectangles is always given by G. So we're going to do G of y minus f of y dy. So this is what we're integrating, but this is going to be a definite integral. So we need bounds. So what do our bounds look like? Are they going to be -1 because -1 and 5 because I think that's what the x values look like? Well, no, I need these points because those are going to be the points that kind of bound this area. But remember, I'm setting up this integral in terms of y, which means my bounds are y values. So because of that, I need to find the y values. So it looks like they're going to be -2 and +4, but we should calculate those instead of reading from this graph. So how do I calculate those? I have two equations here. I know that y is equal to x minus 1 and x is equal to 1/2 y squared minus 3. Here's something I'm going to do. I want to solve for y, so I'm going to re-express this and solve for x. So this is x equals y plus 1. And now I can set these equal to each other. So let's go ahead and solve that equation. So y plus 1 equals 1/2 y squared minus 3. 1/2 y squared minus y. Move that's minus y, move that over as -4, equals 0. Let's double everything, so that becomes y squared minus 2y minus 8 equals 0. I hope that factors. What are some numbers that multiply together to give me -8 and add together to give me -2? I believe that's y plus 2, y minus 4 equals 0. Which that's those, I think those will give you the values we read. So y equals -2 and 4. So now we can set up this integral. This will be the integral from -2 to 4 of g of y. What do we say g of y was? G of y is the line. So that's y plus 1 minus the parabola, which is 1/2 y squared minus 3 dy. So this is the integral. Before we actually evaluate it, let's do some simplifying here. Because there is one pair of terms that combine. I'm also going to put everything in kind of descending orders of powers. So -1/2 y squared plus y plus 4 dy. So I believe this is a good place to stop for B. And I totally ran out of room to do C. So why don't I pause here and figure out where I can buy some of that room back. This was all a means to an end to find the limits of integration, so let's buy that back. Is that going to be enough room? Okay, so now that I have the integral, how do I evaluate it? So to evaluate it, I need to find the antiderivative, and that comes from doing basically the power rule. Basically the first derivative rule you ever learned. Now we're going to do it in reverse. So what's the antiderivative of -1/2 y cubed? That'll be -1/6 y to the third plus 1/2 y squared plus 4y. And we're going to evaluate that at 4 and -2. All right, so when I plug in 4, what I get? I get -64/6 plus 1/2 of 16, so plus 8. Looks like a 9, doesn't it? Don't connect those. Plus 16. All right, then I subtract all this stuff. Plug in -2 for y, I get -8. So that becomes +8/6. Plug in -2 here, I get 4/2. So that's 2. And then -8. All right. So what happens here? Let's combine some like terms. I think I can stay away from my calculator here. First I'll do this. These two things reduced. So -32/3, 4/3. So -32/3 minus 4/3. That's negative 36 thirds, or negative 12. 8 plus 6 is 24. 2 plus 8 is minus 6. Plus, so that's negative 6 plus 6. So all told, I think I got an area of 18. So the area between those two curves is 18. All right, moving on. So I have this region here bounded by essentially 3 equations, and I want to find the area of this region here. So how do I find the area between these two curves? This one we're going to do a little more typically, traditionally. No matter where I draw a rectangle, a dx rectangle, I believe the upper, basically the top end of this rectangle will be dictated by that upper curve. So this upper curve is e to the x over 2, and this lower curve is 1/4 x plus 1. I think no matter where I draw a rectangle, the top curve will be that exponential function, and the bottom curve will be this straight line. So because of that, I think I can set up my integral in just one way. So let's do that. I think we can set up the integral. I'm going to do it in the margin because I think I can just do it in one shot. First, let's do it more generally. I will call this one f, and I will call this one g. So which one is my greater function? In this case, upper. Is it f or g? In this case, it's going to be, so I'll just for now say a to b. In this case, my upper function is f. So I'm going to integrate f of x minus g of x dx. So what is f of x? That is e to the x over 2. What is g of x? That is, and one thing I want to be really careful of here is make sure you put 1/4 of x plus 1 in parentheses. I am almost sure that I'm going to get some people that before are going to have this plus 1 when they integrate. It's going to remain a plus 1, and really it should be subtracted off. We should end up distributing that negative sign to that plus 1. And that's something that's going to be a very common thing to keep an eye out for when you're finding the area between curves, or really any time you're going to be subtracting one whole function from another. You want to make sure that everything in that function, every term in that function gets subtracted. All right, so we're almost done here. The last thing we have to worry about is our interval. Do we know what our bounds are, what our limits of integration are? I think we have a very good idea what our right bound is. We are told that one of the curves, or one of the equations that bounds this, is x equals 3. So I know that my right end is x equals 3. I can also tell you that our left end is going to be 0. So the y-axis is the left end of this curve. So this is a good setup for our integral. I'm going to do one last thing here and actually distribute that negative sign that I went on so long about. So e to the x over 2 minus 1/4 x minus 1 dx. And now from here, I think I am ready to take an antiderivative and evaluate. So e to the x over 2, let's think about this. Maybe it'd be better if I wrote it like this, e to the 1/2 x. What's the derivative of e to the 1/2 x? So the way you do that, you got to think about chain rule. The derivative of any e to the x function is going to contain the original e to the x function. So that would be e to the 1/2 x multiplied by the derivative of whatever the exponent is. So in this case, that would be 1/2 e to the 1/2 x. So essentially you multiply by whatever the derivative of that inside function is. In this case, you're going to divide by that derivative. So this case, because of the antiderivative, so this time becomes 2e to the 1/2 x. And just another kind of check I can offer you here is this. and this kind of is as a general piece of advice I can give you. We've been doing derivatives for so long, and integration is very new. But we also know they're inverses of each other. So if there's ever an antiderivative you're not sure of, do the derivative and make sure you wind up where you started. So we have 2e to the 1/2 x. We said the derivative of e to the 1/2 x is 1/2 e to the 1/2 x. So 1/2 e to the 1/2 x times 2, the 1/2 and the 2 would cancel out, and I would indeed end up right where I left off. Okay, moving on. What is the antiderivative of 1/4 x? Well, the antiderivative of x is 1/2 x squared. So this will be 1/8 x squared minus x. And then I'm going to evaluate all three of these terms from 0 to 3. So let's go ahead and do that. So this becomes 2e to the 3/2 minus 1/8 times 9, so minus 9/8 minus 3 minus what happens when I plug in 0 for all these. 2e to the 0 is just 2 times 1, so that's 2. And then those are just going to be 0. So what do I have left here? I have 2e to the 3/2 minus 9/8 minus 3 minus 2. Can I put all these constants together? Or, I mean, they're all constants, but can I put all the non-e terms together? 2e to the 3/2 minus 9/8. So minus 9/8 minus 24/8 minus 16/8. 49. So minus 49/8. So that's the exact answer I have. I should probably approximate it since I assume many of you are going to do that, and I should be ready for whatever that comes out to be. So 1.5. All right, looks like I got an approximate answer of 2.838. 2.838. All right, so that's the exact answer and a good approximation for it. All right, finally, pharmaceutical company monitors the amount of medication in successive batches of 100 milligram tetracycline capsules and obtains the following graph. Okay, so 10 batches of this medication. So let S of t be a function which represents the specified amount of tetracycline. So that's a constant function. So what's specified, basically what the capsule says on it, or what it's supposed to have in it, is 100 milligrams of the medication. And M is what the measurement actually says is in there. Okay. So that's what those two functions represent. So basically, S is the pink line, the constant line, and then M is the, the jagged series of line segments all joined together. So the first thing I have to do is estimate the value of this integral. So how do I find, what does that integral mean, first of all? So the integral of M of t minus S of t dt, basically what I'm asking here is kind of the opposite direction I asked you to go in the last two questions. So what I'm asking you to do here is to find the area between these two functions. So best I can ask of you here is an estimate, since we can't really get great, yeah, let's just do the best we can. So let's zoom in really far here and do some geometry. So I have a triangle here. How do I find the area of a triangle? We'll call this area 1. Area 1 equals 1/2 times the base, which is, it was like a half. How tall is it? Looks like it goes up to like 9, 8. 1/2 times 1/2 times 8. That comes out to be 2. And I gotta be, ooh, let's be really careful here. It's m minus t, right? Okay, so if the blue is above the pink, those are going to be positive. So, okay, area 1 should be positive. All right, what's area 2 going to be? Area 2 will be right here. That's also going to be a triangle. Area 2 is equal to, be a negative this time. Negative 1/2 times the base, which is going to be also a half, times the height. So 100 down to, looks like it goes down to 91. So 9. Let's be more exact here. I think the negative really got to go there. This will be negative 2.25. All right, now we have area 3. That's a trapezoid. How do we find the area of trapezoids? So that is 1/2 times the base times basically height 1 plus height 2. So we said one of the heights is -9. What's the other height? Let's just say -5. I'm going to use whole numbers for all these. So this comes out to be -14, -7. All right, then area 4. That's going to be another trapezoid. So 1/2, again, that's another, the base is 1. The heights are going to be -5 and -6. So that'll be -5.5. Area 5, what does that look like? That'll be this guy here. Why am I circling? So 1/2 times the base, which is a half, times the height, which is, we said it was -6. So that'll be -1.5. Area 6 will be here. That'll be 1/2 times 1/2 times the height, which is, I think it's +6. So that'll be 1/2. Area 7 is another triangle. So area 7 is equal to 1/2 times the base, which is going to be 1, times the height, which we said was 6. So that area was 3. Let's take this whole thing as a triangle. By the way, like, however you estimate it, I'm probably going to be okay with. So what is this base length? It's not quite 2. Let's say it's 1.6. And the height we said, we haven't said this height yet, have we? The height is looks like 9. Now we'll say 8. 4 times 1.6, that's 6.4. Okay, where's our next area? 9. Area 9 is equal to something really tiny. That'll be 1/2 times 0.4 times -3. Why not? That's -0.6. All right, next. Area 10. What's that equal to? So that'll be another trapezoid with a base length of 1. What are the heights? We said that one was a -3 on the left. And what's this other one? I think that goes down to, let's say, 92, so -8. So -11/2 will be -5.5. And we're almost done. This is another trapezoid. Area 11. So 1/2 times the base length, which is 1, We said the lower height was negative, left height is -8. What's the right height? The right height is going to be so small. We'll say it's -1. So that'll be -4.5. Awesome. Got them all. Now let's add them all together and see what we wind up with. So 2 minus 2.25 minus 7 minus 5.5. Next two cancel out, not entering them. Plus 3 plus 6.4 minus 0.6 minus 5.5 minus 4.5. Okay, so here's what I got for a final result. I got that this value, by my estimation, is -13.95. So if you're, if you're close to this, great. I mean, I'm probably going to be pretty liberal with what I call a correct answer. I do think it's going to have to be negative, though. So what does this answer mean? What did I just find? So I found that the value of this integral, let's say -14. The value of this integral is -14. What does that mean? What that means, I believe, is that basically this person, well, let's figure out what I measured here. What is this thing saying? This function is giving me the number of milligrams per dose. And I integrated it over 10 doses. So I think what I found is that over this batch, or like over this like sequence of 10 doses, this person or this patient, whatever I'm measuring here, they received 14 fewer milligrams of the drug than the specifications called for. I think that's a good way to interpret what this integral that I just estimated is. All right, that's all for checkpoint number 13.